Hey guys, so I'm sorry to miss you today, but hopefully these notes will allow you to move through the two sections we're going to have a look at. We're going to focus on traversable graphs, and you might be asking, what is a traversable graph? Well, in order to know that, you need to know what the word traversable means. So if we have a look here, traversable. Adjective form of traverse. Well, we need to know what to traverse means. Okay, to travel across or through. So essentially when we're having a look at these networks here, what we're wanting to know is, can we travel through this network? Okay, so a traversable graph has a trail that includes every edge in the graph. So can we travel through this graph visiting every single edge? Okay, now the graph opposite, this one here, graph 1, is an example of a traversable graph. It has a trail that includes every edge. And if you have a look here, if we map it out, let's get a colour. I haven't tried this before. Oops. If we start at A, we can go B, C, back up to A, and back down around till C. Now, it doesn't matter that we've revisited vertices. What's important is that every edge has been visited. Okay? So, I think we just did the one that they suggested, A, B, C, A, C, okay? But not all graphs are traversable. For example, it is impossible to find a trail in the graph opposite, so looking at graph 2, that includes every edge. Try and see. So I'll give this one a crack. I'll go D to B to C, back up to A. Oh, and as soon as I get back to B, I'm going to have to revisit an edge. We'll have another go. I'll try from somewhere different. B, C, A, B, oh, and I've still ended up with an unexplored edge on AD. So that's why this one is not traversable. Okay, now there's some clues, because the last thing you want to do is to be guessing and checking every single possibility, essentially. What you need to be able to do is implement this. So there's some rules for identifying traversable graphs. So first of all, it has to be connected. Okay, we can't have an isolated vertex because it means we cannot travel to it. Okay, what we want to have a look at is a connected graph is traversable if all vertices are of an even degree. Now, hopefully you're rushing back in your notes going, oh, what's degree again? I'll pause for you to go and have a look, because I hope that's one of those key things that we need to know. So go back and look at what a degree is. Okay, so we either want all the vertices to be of even degree or exactly 2 vertices of odd degree and the rest are even. Okay, it's not up to 2, it's not more than 2. Exactly 2 of those vertices are of an odd degree, the rest have to be even. Okay, so from this, it follows that a traversable graph will either have a trail, a circuit, or a cycle that involves the use of every edge in the graph, okay? And we can know straight away if a graph has more than 2 vertices of odd degree, it is not traversable. And we can check this on here. If we jump up and have a look at the degree of this, well, there's 1, 2, 3. A degree of 3 at vertex A. We've got 1, 2, a degree of 2 at vertex B. So if this is traversable, okay, we need exactly 2 of odd degree. So we need this bottom one to be odd as well. And let's have a look. 1, 2, 3. So we can see using this rule or this pattern that's been discovered that when we've got the exactly 2 odd, okay, and just 1 even, or the rest being even, it's traversable. Now this one was non-traversable, and we could have kept on going and guessing and checking, but if we knew the rule, we could check it by inspection. We wouldn't have to go through. So the degree of this one is 3, and double check, we can see we've got 1, 2, 3 edges leading into this vertice. This has got a degree of 3, and as soon as we realise this one here has a degree of 3, we realise it's not traversable or non-traversable because we've got more than 2 odd vertices. And just to finish it off, we've got the 3 here. So all of these are odd vertices. We know, vertices of odd degree. We know that this is a non-traversable graph. Okay, so the key component, this key idea that we've got down here in this little box, okay, the key component of determining if a graph is traversable is to identify the degree of each individual vertex. That's the number of lines coming from each vertex, and that's what we just did up here in the above example. Rightio, so let's do some examples. Let's see how we can apply this. Sorry, just changing slides. Beautiful, and I've just left that key idea up there. So for each of the following graphs, determine whether the graph is traversable and state why, okay? If traversable, check by identifying a trail or circle that travels through that graph. Okay, well, for me to do that and me to be able to talk about possible trails or circuits, I need to be able to identify these vertices. So that's what I encourage you guys to do. So if we just flip over to this slide here, sorry, it's a bit dark because I've just done a screenshot, but essentially they're the same diagrams. All I've done is label these vertices. Okay, so the first thing we need to do is determine whether the graph is traversable. Well, in order to do that, we need to have a think about what the degrees of each of these vertices are. So if we have a look at A, got a degree of 2 because we've got the 2 paths, okay, 2 edges, I should say, leading into the vertice A. Same with B, got the 2 edges leading into the vertice. Same with C, and same with D. And if we look there, all of these have an even degree, which means, yes, it is traversable. Okay, I'll pop the notes and show you our annotations in a moment. We'll just go through and have a look. Okay, if we look here, we've got 2, 2, 3. Oh, so we've got an odd one. It means there has to be only one more other odd vertice. And we can find that over at E, who also has a degree of 3. This means that A has to be even for this to be traversable. And if we have a look, 1, 2, we've nailed that there. Now we'll jump around and have a look at these ones here. We've got a degree of 3, a degree of 3. Oh, we're already at our 2 odd degrees, and we can see here, oh, well, here's a 2. Looking good, we might be able to hang in there. But as soon as we get to here, we've got that degree of 3 and that degree of 3. So this one here is not traversable. Let's have a look at how we actually travel through this. So we've been able to determine whether the graph is traversable or not, and the reasons why. Well, this one, all of the vertices are of an even degree. Exactly 2 are of odd degree and the rest are even in this second example. And this one is not traversable because we have all of those vertices of odd degree. Now, let's identify a trail and circuit that traverses this graph. Let's put this into practice. So we'll start at A, and what if I go A to B, B to C, C to D, and D to A? Beautiful. We've covered every edge. Excellent. We haven't repeated any edges. We don't want to be doing any walks here. Okay, look back to last lesson if you're getting mixed up between trails, paths, walks, circuits, cycles, okay? So we've got every edge has been visited, and you'll also notice that we've ended at where we started, okay? So we've ended where we've started here. Beautiful. Let's have a look at example 2. So if we have a look at example 2, we've got to be really careful because we've got some that are even and some that are odd, and it matters where you start. When you're dealing with these ones that have got the 2 odd vertices, you have to, you don't really have to, you have to start at one of the odd ones and you'll finish at the other. So I could decide to start at D and finish at E, or start at E and finish at D. Did I do that? I'm all mixed up. I'm gonna pause. Beautiful. So if we have a look at this one here, let's traverse this one. Oh, where'd my little pen go? Here we go. So we'll start at E. Let's go E, D, A, E, B, C, D. And you can see here, even though it's poorly drawn, we've covered all those edges, okay? This time we haven't ended up at the same location though. We started at E and end up at D. And this one here, we know it's not even worth starting to guess and check because we're only going to run into failure. This is similar to the Königsberg Bridge problem, okay? No matter how many different ways you approach this, we know because of these extra odd vertices that this is not an achievable task. And that's what makes these rules so helpful and so handy, is that they can avoid us a lot of unnecessary crunch work. Cool, so this will allow you to go on with your notes relating to 9F. So there's no worksheet attached to this one, guys. You literally just have to jump in and continue with that bookwork that's on the log sheet. All the best, and I've got a second video for you for lesson 6. Okay, that's looking at 9G. So it's really related to this lesson. So they'll flow on nicely if you want to watch them next to each other. If not, take a break and you can watch that second lesson when it suits you. Thanks, guys.